just don't know what to say, Wayne.
I'm all out today.
Yeah, no funnies left.
No.
No.
So we normally start a video with a bit of a joke, a bit of a stupid mess around to make revision fun.
But we just didn't have any today.
There was that internal joke though.
Yeah, that was...
You wouldn't have got it.
No, that was that potential joke, which is still potential, so it's not happening.
There was the ideal gas joke, that was relevant,
that was
but it's
a good
just
one.
not going to happen.
It's not going to happen. We don't have a Canon at the Progress Squared Studios, so the kinetic energy joke is just out the window, isn't it, Wayne?
Yeah.
Probably the problem, because if we had the Canon, we could get out the window.
Yeah, you're right.
Yeah, you're right.
Just all out of energy today, I guess.
Yeah.
Just gone with it.
So it's about internal energy.
Yep. If you can think of a joke about that, please let us know.
Yeah, please let us know. But we're out of those. So what is internal energy?
It's defined as the sum
Yeah.
of the kinetic energy.
Oh, so let's do KE. So it's quicker.
K, that's a terrible K, but it is a K.
It is a K.
Kinetic
And
energy.
potential energy.
Yeah.
So these two things are related in many things. At first, let's think about the ideal gas again. But what is that, Wayne?
An ideal gas is a gas that doesn't have the potential energy thing. It's only reliant on the kinetic energy.
Yeah. So you say that there's no relation of things between the intermolecular forces.
Yeah, there's no intermolecular forces and stuff. But if you apply pressure to it and it keeps going down, eventually it can occupy no volume at all.
Which is ideal.
That was ideal for math. That'd be really easy.
It'd be great, but that doesn't happen, sadly.
But you need to be aware of what an ideal gas is.
Yeah, because your concepts rely on it.
Yeah. But in real life, it's kinetic energy and potential energy.
Mm.
That's what happens with actual stuff, gases and stuff.
Yeah, and because they're the sum of these two things, different factors affect each one of them will affect the total internal energy.
For example, you know that if you raise the temperature in a system, you're going to give the particles more energy and they're going to move around quicker. And
Yeah.
you know, because kinetic energy is a half mv squared, if the speed increases, that increases. So temperature will make that bigger, and if that's bigger, then
Yeah.
internal energy will be bigger.
So that's one.
That's
Then we
one.
have pressure. Now this affects both a little bit, but it also involves our potential energy.
Yeah, because like we said, for an ideal gas, if you increase the pressure, nothing would happen to the internal energy. It wouldn't
No.
change.
But as gases are not ideal, that does happen.
When they get really, really close together, there's going to be more intermolecular forces because the dipoles are going to be closer together. It's going to cause greater things.
Yeah, and then when you release that, they'll then spread out, and no kinetic energy has changed there. That would be the potential.
So that's pressure.
Yeah.
I'm not going to do it. Yeah, I'm going to do it in blue.
Yeah, do it in blue.
So pressure.
And finally, we have states.
Yes. Now, when you change from a solid to a liquid and a liquid to a gas, the kinetic energy actually doesn't change, but the potential energy does change as you're changing from one state to another.
Yeah.
So as you change from one to the other, the internal energy is increasing, but in the form of the potential energy. That increases greatly at that point. And we can express that with a graph.
We can. So I'll draw a graph up.
Okay.
The
I'll keep that up.
opposite of that one. So let's use water. I think we used this in a previous video.
Yeah. So it goes down
Yeah.
a little bit below zero.
Yeah.
So this is temperature in degrees.
Yes. And this is time
Degrees Celsius. That's time.
in seconds. So this point.
Yeah, you know
it
that's the
goes
freezing point of water. So it's going the other way. So
flat. Mhm.
it's going to turn into a liquid at that point. You know it goes flat before rising again. This would be 100 degrees, which is the boiling point.
Yeah. And then again it would shoot up again. And during these changes there are different energy changes.
There are. So as it's increasing, the temperature's increasing.
Mhm.
And we know that that's related to the kinetic energy. So from here to here,
Our kinetic energy
here to
is
here, and
changing.
yeah, our kinetic energy changes.
And in these parts,
Yeah.
when potential energy will change.
Yeah. So as it stays horizontal or vertically horizontal, which is a weird thing to say, vertically horizontal, but I mean pretty much horizontal.
Mhm.
The potential energy changes, but the kinetic energy actually stays the same.
So, because of these two things, internal energy is actually rising all the time. So, if we were to do a graph of that, it would be a straight line.
Yeah. Don't
If
put
I
your pen
had.
too far.
Don't need that.
So internal energy increases all the time, and that's this video in a nutshell, really. But the ideal gas is an important concept.
Mhm.
So I'm looking at that graph up there.
Yes.
Jokes against time.
Now, I've extrapolated that one way.
Oh, good.
So, it looks like it just goes down and down and down, but I think this is a minimum that way there.
Right.
So, I think that our jokes against time,
Jokes against time. Jokes.
so at
against
the moment it's going down like a lot. It's not
Yeah.
quite the same
time.
as
So
that.
hopefully this is like today.
Yeah,
Couldn't
this
think of anything
is a
funny.
minimum. But I think, pretty sure it's going to do that. Pretty sure.
Okay,
Yeah,
good.
yeah. There's some maths and that's what's going to happen.
Tell you what, I'll have a cup of tea, and for once I'll actually have one sugar in it to give you some energy. Just to
Good
mix
idea.
it up.
Yeah, internal energy will eat more jokes.
Exactly.
Not internal jokes though.